Welcome to Math 31, and we are in Chapter 7 looking at derivatives of trig functions, and we're in 7.4 looking at applications. This is the last section that we'll be doing in Chapter 7. The sections beyond this are not critical for us. We could figure those out at some other time, just not a priority for the time that we have this year. We're going to look at 4 examples. The first 2 will be optimization questions, which are where we're looking for minimum and maximum values, and the last 2 will be related rates questions. So let's look at question number 1. Suppose we have the position of a particle. It's moving horizontally, and its motion, or its position, is described by this s of t function, sine squared of t minus cos t, over this domain from 0 to 2 pi. So s is the displacement in meters, and t is the time in seconds. We want to determine the absolute minimum and maximum displacements. So what's the farthest that our particle gets away from the position of 0? So when we're looking for absolute minimum and maximums, you will recall that we started by finding the derivative of the function. So again, derivative of sine squared, bring down the 2, keep the sign unchanged, times the derivative of the sine function, which is cosine of t, minus the derivative of the cosine function. Derivative of cos is negative sine, so subtracting the negative gives us a plus sine t at the end of our derivative here. And we're interested in the endpoints, so 0 and 2 pi. And we're also interested in critical points where this derivative might be undefined or where it's equal to 0. Well, sine and cosine are defined for all real numbers, so we're really only interested where is this derivative equal to 0. And I've already pulled out the common factor of sine t, so I have 2 factors giving me a product of 0, so I'll set each factor equal to 0 and then solve. So if sine t equals 0, then t could be 0 pi or 2 pi. And you might recall, probably thinking of this graphically is probably the easiest way, at least in my head, to think it through. So if I picture what does the sine graph look like, sine starts on the origin, curves to a maximum first, to a minimum, and then back here. And all of that happens in a period of 2 pi. Halfway in between is at pi. There we're at 0, so where's our function equal to 0? At 0, pi, and 2 pi. And again, double checking our domain up here, we have less than or equal to, and again, less than or equal to, so we're including those endpoints. Then where we see the cosine of t is equal to negative 1/2, we have a few options for how we may solve that. One of the options that some of you will have used in Math 30-1 is the unit circle. And you'll recall that the cosine of an angle is the x-coordinate. And so I'm looking, where do I have an x-coordinate of negative 1/2? Well, there's a negative 1/2 at 2 pi by 3. Here's a negative 1/2 at 4 pi by 3. So that's one way we could get this. Another way that you may have done it if you thought about the special triangles instead is if cosine is negative 1/2, we would think of this as x over r. My r value is always positive, so my x value will end up being negative, so I'm going in the negative direction 1 unit. And I'm setting up my triangle here-ish, where this would be my r value of 2, and, ooh, that's scary, an r value of 2. We'd get a reference angle here. This would be a √3 positive and a √3 negative. And this would be a 30, 60, 90 triangle where this would be 60 degrees as my reference angle here. Or in radians, that would be a pi by 3. So if I do pi minus pi by 3, I'll get the 2 pi by 3. And then pi plus a pi by 3 will give us the 4 pi by 3. So a couple of ways we could get those values. So we have 5 different critical points in the domain that we're given for this question. So what we want to do now is think about for these 5 values we have. We typically didn't use a number line, but I'm going to use a number line this time. And these are my t coordinates. I need to figure out, well, what is my position at each of these points? So these are the y values. If I think of this as the x values in blue, the y values are in black. And I want to see what's the biggest and what's the smallest y value. So in this question, because we're looking for both maximum and minimum displacements, the minimum will be the negative. Well, where did these numbers come from? Well, I plug in 0 in for t, and that will give me a negative 1. So maybe I'll demonstrate here with this. If I have a 2 pi by 3, and I plug that into my function, then I have sine of 2 pi by 3 all squared. This is my original function, right? So I'm not plugging it into the derivative. It's the original function up here, sine squared of t minus cos t. So here I have the sine squared of my t value, 2 pi by 3, minus the cosine of 2 pi by 3. And then again, using the unit circle or special triangles, the sine of 2 pi by 3 is going to be root 3 over 2. That's going to be squared to give me 3/4. And then the cosine of 2 pi by 3 will be a negative 1/2. Subtracting the negative makes it addition, get a common denominator, add the numerators together. There's my y coordinate that corresponds to my t value. So this 5/4 is my position at a time of 2 pi by 3. That's the maximum, right? So 5/4 is 1 1/4. That's bigger than 1. So that tells me that my maximum displacements will be happening here and here. So those two will be max displacements. And then for the minimum displacement, I will look to see, well, the farthest I go negative is to -1, and here also to -1. And you'll remember those endpoints are within the domain that we were given, and so they are acceptable solutions for this question. So my maximum displacement is 5/4, and it happens at 2 different times, at pi by 3 and 4 pi by 3. Minimum displacement is -1, and that happens, where that happens is when t is equal to 0 or 2 pi. So we have answered the question. Let's move on to example 2. So this question should look familiar. It's from 4.4, question number 20. It was on page 191 in your textbook. When we did this question, well, when you did this question, in some classes, the question came up and we went through it together, but not in every class. The way that we did it was not using trigonometry. But I want to show you as we work through this question that trigonometry probably makes it a little bit easier than using similar triangles. So here's the situation. We have this painter on a ladder painting the exterior to this wall, but the ladder needs to reach over top of this covering that's on the sidewalk. So the sidewalk, as we can see here, is 2 meters wide, and this covering is 3 meters tall. Wow, she's a very tall woman. Like 80% of 3 meters. Wow, that's amazing. Anyhow, diagram, not to scale. So we want to know what's the shortest ladder that will get over top of this corner and reach the wall and still be safe. So if we look at kind of a side view diagram, this is what we see. So here the hypotenuse is the ladder, and then here this rectangle at the bottom is that corridor that goes over top of the sidewalk. And you can see where I've introduced an angle theta here. And theta will be the same because this angle continues all the way along, and this is compared to horizontal, Therefore, the angle between horizontal and the hypotenuse is the same for the green and for the blue. And then we have these lengths. So this width is 2, this height is 3. What we want to do is minimize this total length. So I've broken it down into length 1 and length 2. So as I look at this top triangle here, cosine of this angle will be adjacent, the 2, over the hypotenuse, L2. And if I rearrange that, I will get L2 is equal to 2 over the cosine of theta, or 2 times secant of theta. And I'll do something similar for this bottom triangle, where I will get L is equal to 3 over sine theta, or 3 cosecant theta. So I have an expression for length 1 and for length 2. Our goal is to minimize the sum of those two lengths. So the total length will be length 1 plus length 2. Length 1, 3 cosecant theta. Length 2, 2 secant theta. Well, here I have my function where the length is a function of the angle. Since I want to find a minimum, I will take the derivative of this function. So here we go. 3 times the derivative of cosecant, which is negative cosecant theta cotangent theta. And the derivative of secant theta is secant theta tangent theta. So there's my first derivative, which I will set equal to 0 in order to determine values of theta where I'll have a minimum or a maximum. So as I rearrange, I'm taking this blue part, I'm adding it over to the left side of the equation. And then I'm rearranging. So I'm going to take this cosecant theta cotangent theta, divide it on the right side, and take this 2 that was on the right side and divide it over on the left side. So I get all of my trig functions together on one side of my equation. Now somehow I want to be able to get this down to a single trig function. So I'm going to use some identities. Secant theta is 1 over cos theta, so there's my cos theta in the denominator. Cosecant theta is 1 over sine theta. Since I'm dividing by 1 over sine theta, take the reciprocal and multiply, and I get this sine theta in the numerator. Similarly, this cotangent theta is 1 over tangent, and since it's in the denominator, take the reciprocal and multiply, and that'll give me a tangent squared theta. You may need to pause the video at this point just to convince yourself that this right side is correct. So if you're not convinced, you should pause now, do the algebraic manipulations to convince yourself that this is correct on the right-hand side. Well, next, this sine theta over cos theta is a tangent theta, which gives me tan cubed theta equals 3/2. Well, to solve this equation, I will need to cube root both sides of the equation. And once I've cube rooted, I can do the inverse tangent of, I'm missing here, but I should have, I'll do it in red. There we go. The cube root of 3 over 2. Now, am I in degrees or radians? I'm in radians, and to be on the safe side, it's good to just always work in radians, especially for application questions, although for this question, it wouldn't actually matter. We could do it in degrees. So if I get that value for theta, then I can go back to my original equation up here. Let's look at this one, where my total length is 3 cosecant theta, or 3 over sine theta. plus 2 secant theta, which is 2 over cosine theta. And that's what I plugged it into down here, since my scientific calculator won't do cosecants or secants. So 3 over sine of my theta value, 2 over the cosine of my theta value, add them up, and I get 7.0 meters for my length. Well, is this a minimum? Well, let's do a couple test points. So we'll do our number line here. Maybe I'll move it down a little bit. There. Extend our page. And we had the critical point where our theta value was 0.85-ish. So we can do a test point to the left of that. Let's go with 0.5, and to the right of that, 1.0. Now, just before I go on, I should think, are both of these values within the domain? Well, my angle is going to have to be bigger than 0, and it'll have to be less than 90 degrees, so less than pi by 2, and pi by 2 is about 1.6, 1.57. So those would be my outer limits for what the angle could be, so the 1 and the 0.5 fit in there nicely. And then as I compare my lengths, so these are theta values, these are lengths. Here at 0.85, we got 7.0 meters. Here, if I plug in 0.5 into this same function, so I do the sine of 0.5 in the denominator, cos of 0.5 in the denominator, I would get a 7.3 here. And if I plug in the 1 in place of theta, I'll get an 8.5. So then I can see that, yep, this is a minimum. So there's my solution. 7.0 meters is the minimum length for that ladder. On to a different type of question. A related rates question. So we have two sides of a triangle, and we know their lengths, 3 meters and 5 meters, and the angle in between them is increasing. And here's the rate that it's increasing at, pi by 10 radians per minute. How fast is the length of the third side changing when the angle between is 45 degrees? Well, kind of a weird question that we have some of the information in radians and some in degrees. That's unusual. But we'll just set that aside for the moment and look at a diagram. So I have one side is 5, one side is 3, and this angle in between is increasing at this rate, pi by 10 radians per minute. So I know that d theta dt, pi by 10 radians per minute, it's increasing. So this is a positive rate of change. So notice it's a derivative with respect to time, a related rate. Time doesn't show up in the question other than in a rate, radians per minute. We want to know how fast this third side x is changing, so we want to know what is dx dt. How does that length change as time changes, as time increases? Well, if this angle is getting bigger, this x should be getting longer as well, so we're expecting to get a positive value for this dx dt. Well, where will our equation come from? It's not a right triangle. We can't assume that it's a right triangle. And so we can't just use a simple trig equation. We'll need to use either the sine law or the cosine law. We have this opposite side. Looking at the formula sheet, oh dear, there's no cosine law. So let me just remind you, this is what the cosine law would look like for this question, where we'd say the length of the side opposite the angle we're interested in, if I square that length, x squared, it's equal to the other two sides that I know, the two adjacent sides, adjacent to this angle, 3 squared plus 5 squared, minus 2 times 3 times 5, times the cosine of the angle that's in between these two known sides. So if you needed the cosine law for a question, I guess I'd have to give it to you on the test or in the assignment. Well, let's actually evaluate what is x equal to. So if I square root both sides and I simplify, 3 squared is 9, plus 25 is the 34. And then 2 times 3 times 5 is 30. And we're interested when the angle is 45 degrees. So I plugged in that 45-degree angle right away. We know the exact value for a 45-degree angle cosine is the square root of 2 over 2, or you may think of it as 1 over square root of 2. Either is fine. This I reduced a little bit. The 30 divided by 2 gives me 15. So there's the length of x at the instant when this theta is 45 degrees. So what we've been doing so far is just setting up the question. Now we want to know how is x changing as theta changes. So we'll go back to our equation that we have up here, and we'll take the derivative of both sides. So that's what we have here rewritten, the original function, and we take the derivative with respect to time. So derivative of x squared is 2x dx dt. Remember, this is a chain rule. I'm assuming x is a function depending on time. So I multiply by the derivative of that inside function. Similar on the right side. Here I have the 30 times cosine theta. Derivative of cos is negative sine, but I was subtracting here, so the two negatives canceled out. These two were constants, so their derivative is just 0. So that's why they've disappeared. So derivative of cosine of theta is negative sine theta times the derivative of the inside function d theta dt. And there's a relationship that relates these two rates together, hence a related rate question. We want to solve what is dx dt equal to. So when we divide both sides by 2, this 30 will become a 15, and we'll get an x in the denominator. And we know that our theta value will be 45. Our x value we figured out above, here in blue, square root of 34 minus 15 root 2. So we can substitute those into our equation. Same thing with this d theta dt is a pi by 10. And when we evaluate, we get 0.14 meters per minute. Now, where do the units come from? Well, let's think about it here for a moment. Let's start with this 15. Where did that 15 come from? Well, it came from here doing 2 times 3 times 5. We knew that this length was 3 meters, this length was 5 meters, so the 3 times 5 is meters times meters, which will give me meters squared. So here I have units of meters squared. Sine of an angle is a ratio. A ratio of lengths means it has no units. So my numerator is just meters squared. In the denominator is the x. The x is that third side of the triangle up here, which is going to be a length in meters as well. So in this denominator, I have meters. And then this angle we were given in radians per, what was it, per minute. Now you'll remember that a radian is a ratio of lengths. It's the ratio of the arc length compared to the radius, so a radian has no units. So the units I have here are just something per second, or seconds to the negative 1. So as we look at this, we can see the meters will go into meters squared a meter time. So I'll get meters times meters to the negative 1. Oh, not seconds, this was minutes. Whoops. Be careful, Mr. Wagner. So that'll give me meters per minute as my units here. And if we wanted to convert that to 14 centimeters per minute, well, that would be acceptable too. So there's the rate of change in that third side of the triangle. With respect to time, we got a positive, which is what we expected. And as this angle gets bigger, so does the length of this side. One more question. Another related rates question. Suppose we have a plane. It is maintaining a constant altitude of 600 meters. So this is going to be a constant, so I put in a number instead of a variable. It's going to fly directly over an observer, and we're going to have the observer at this point, and then the plane directly over the observer here, and then it's going to fly away from the observer in that direction. So we'll have this angle theta here that's changing as that plane moves, and this x is this horizontal distance between where the observer is standing here and a point directly beneath the plane. So this observer is doing something a little illegal, shining a laser on the plane. Dangerous thing to do. We want to find the speed of the plane if the angle between the laser and the plane is changing, so the laser and the horizontal. So this angle is changing at a rate of 4 degrees per second. We're interested in all of this happening when we know this angle is 60 degrees. So at that instant in time, how fast is this plane traveling? Well, theta dt we know is 4 degrees per second. Why did I make it negative? Because as this plane flies to the right, this angle is going to get smaller. But wait, how do I know what direction the plane is traveling? Well, I don't. In the way I drew the diagram, I made an assumption that the plane is flying away from the observer instead of towards. So if we think about this happening, as the plane flies in this direction, this horizontal distance is going to be increasing. So I expect that this will be a positive value. When I solve for dx dt, that's going to be the speed of the plane. The plane is traveling horizontally. How fast is this horizontal distance changing? That's the speed of the plane. If the plane was traveling in the other direction, this d theta dt would be positive, but then this x would be negative. So all I really need to recognize is that these are changing in opposite directions. If the angle is decreasing, so a negative rate of change, then dx dt will be positive, increasing. And similarly the opposite. If this angle was increasing, positive 4 degrees per second, then this dx dt would be getting shorter, lessening, decreasing, so we'd have a negative rate of change. We're just asked for what's the speed of the plane. So no matter whether we get a positive or negative here, in this case it should be positive, we're just interested in the size of this value, not in the sign. So that's why it's not a problem for us to introduce the assumption of direction in how we drew this diagram. Now, important thing to keep in mind, we're going to have a d theta dt in our equation. In the previous question, it was fairly handy because when we got to the end, we had radians per minute as our rate of change in the angle, and a radian doesn't have units. And so it didn't mess with the units in our final answer. So we need to change this to radians so we don't introduce units of degrees. So to convert that to radians, I'll multiply by pi over 180 degrees and simplify it to get negative pi over 45 radians per second, keeping in mind the radians is not a unit, it's a ratio of lengths, so this is just a per second value. Well, now we need an equation that will relate this side length x to this angle theta. And it's not a difficult equation. We have opposite and adjacent, which means we will want the tangent of theta is equal to 600 over x. Now, I'm just going to calculate an x value quickly. If I rearrange this, I'll get 600 over theta. I'm told theta is 60 degrees. Now here, because I'm plugging the value into the trig function, it doesn't matter if I'm in degrees or radians. The tangent of 60 degrees is root 3. The tangent of pi by 3, also root 3. So the value that I get here in this expression is the same whether or not I use degrees or radians inside the trig function. It's only for this d theta dt that's going to be outside of the trig function, where I have to make sure that it's in radians rather than degrees. Well, let's get into the calculus. Here's my relationship. I've just rewritten this x in the denominator as x to the negative 1 to make my derivative a little bit easier. Derivative of tangent theta is secant squared theta times the derivative of that inside function d theta dt. On the right side, bring down the negative 1, subtract 1 from the exponent, so I have a negative 2 in the exponent, times the derivative of the inside function, dx dt. Our goal is to figure out dx dt. That's going to give us the speed of the plane. So as I rearrange here, I will divide by this negative 600. That's where this comes from. So this x to the negative 2 is actually an x squared in the denominator that'll get multiplied up into the numerator with the secant squared theta. So that's why it's up here, still having the d theta dt. And then I can substitute the values that we worked out. So x, as we figured out up here, 600 over root 3. That 600 over root 3 is being squared. We're interested when theta is 60 degrees, so again, I didn't bother converting that to radians because it's going inside the trig function. You can convert it to a pi by 3 if you like. That's going to be squared over top of the 600. Now, in this line, I also kind of brushed over detail. So let me just quickly highlight what I did. As we look up here, this 600 was a negative. But you'll remember also our rate of change in the angle was also a negative. So I just multiplied those two negatives together and ended up ignoring them. So again, reminder up here, we had that negative pi by 45 radians per second. So those two negatives ended up canceling out, and so I didn't initially write them in. But to be careful, that's where it came from. Then as I evaluate here, what have I done? Well, if I square this, squaring this square root of 3 gives me a 3. This 600 is squared, but it's also divided by a 600. So I just reduce that to leave me with the 600 in the numerator. And secant squared of 60 degrees is equal to 4. So again, if we do a bit on the side here, we'll remember that cosine of 60 degrees will be 1/2. So secant of 60 degrees will be 2. And since I have secant squared, I'll have 2 squared, which is where this 4 is coming from. And then it's multiplied to the pi over 45, and the negative times negative gave me a positive. If we want an exact value answer, there we go, 160 pi over 9. Quite likely we'll be interested in a decimal approximation, and this works out to be about 55.9 meters per second. Again, let's just think through the units to see where the units of meters per second are coming from. Here we'll go with yellow. So this 600 is in meters. It's being squared. The root 3 didn't have units. So this is a meters squared in the numerator. Secant is a ratio, so there are no units. This 600 is meters. And then this pi by 45 was radians per second this time. And so it's just seconds to the negative 1. And again, the meters will reduce. Meters squared divided by meters just gives me meters. And then seconds to the negative 1 is per second. So that's where the units come from. And that ends this example. It ends this section and ends the chapter. So, time to do some practice.